What lies beyond the universe? Let's delve into the structure of the universe to shed light on this matter. When we discuss the structure of the cosmological model of the universe, the first thing that comes to mind is the observable universe. Typically, when we refer to the universe, we are talking about the observable universe. Imagine this as the part of the universe we can see in all directions from our perspective. However, this notion is not entirely accurate. Although it's called the observable universe, it doesn't mean we can observe everything as we wish. A significant portion of this universe is visible only as it appeared in the past. You might be aware that the observable universe has a radius of about 46.5 billion light-years. Given the age of the universe is around 13.7 billion years, this might seem illogical. However, remember that the universe is continuously expanding. As long as the distance between 2 points is sufficiently large, the new space that emerges between them due to the expansion could make them move away from each other at speeds exceeding the speed of light. This faster-than-light expansion due to cosmic expansion doesn't violate the rule of moving faster than light. It's more like the path taken by light gets stretched, creating a visual effect of faster-than-light motion. Consequently, many regions we observe, such as those high redshift quasars, are actually moving away from us at superluminal speeds. What we see of them is how they appeared a long time ago when they were closer to us. Their current appearance is beyond our reach because the photons they emit now, even if traveling at the speed of light, are much slower than their rate of moving away from us. Thus, the observable universe's exterior seems similar to what we've already observed, but due to the vast distances involved, it's beyond our current observational range. However, the regions beyond the observable universe might not remain forever unseen. Ignoring technological limitations, regions adjacent to the boundary of the observable universe are still sending light towards us. In time, this light will eventually reach us. This implies that our observable universe will expand over time. Theoretically, we might witness scenes from beyond the universe that were previously inaccessible. While we could potentially see more galaxies in the future, there's a caveat. The wavelengths of light from galaxies are being stretched due to cosmic expansion, resulting in larger redshifts. Similar to the concept of approaching the event horizon of a black hole, these galaxies will appear increasingly red, fainter, and eventually disappear from our view. Although universe often refers to the observable universe, as mentioned before, the observable universe might be just a small part of the whole universe. The entire universe could potentially possess an infinitely vast expanse. Each observer within this universe might have their own observable universe, all adhering to the same physical laws. While these laws are the same, each observable universe might have different initial conditions, leading to variations in matter distribution, evolution, the emergence of galaxies, planets, life, and civilizations. This concept aligns with the notion of Level 1 parallel universes proposed by Tegmark. If the universe is indeed infinitely vast, there would be a parallel universe, identical to ours. In that universe, there would be another you, watching the same video as you. According to the theory of eternal inflation, the distance between you and your parallel self would be just 10 to the power of 10^29 meters. Is it close? Is the probability significant? You might find it difficult to grasp the enormity of this number. Even representing each zero with a pixel, you'd need more than 3 billion 8K displays to show it. Now you understand why the premise is an infinite expanse, right? So, has the vastness beyond our universe exceeded your imagination? But is that all there is? Even if we include a universe with another you, as well as all the observable universes, this would still be our universe. According to the theory of eternal inflation, our universe, which includes all Level 1 parallel universes, is just a small region within a larger universe. And similar areas or universes are infinitely numerous. Previously, I mentioned that beyond our observable universe lies a region similar to our universe. However, these regions are incredibly distant, so much so that the speed of the light emitted from them at the beginning cannot catch up with the expansion of space. As the space in front of them continues to inflate exponentially, their images will never reach us. If there are extraterrestrial beings in those places, they exist beyond our observable universe, and similarly, we are outside their observable universe as well. Nevertheless, whether humans or these extraterrestrial beings, we all exist within the same universe. Let's call it the home universe. Clearly, the home universe is vastly larger than the observable universe. Earlier, I mentioned the shape of the universe. Based on measurements of the curvature of the observable universe, if the home universe is a closed sphere, then the nearly zero curvature we observe implies that the observable universe is comparable to a small flat region on Earth compared to the entire planet. Now, does the home universe have an exterior? What might be beyond it? Do you remember the inflation theory? This theory tackles two main questions. 1. Why is the universe so uniform? 2. Why is the universe so flat? The inflation theory proposes an answer by suggesting that at the universe's birth, there was an immensely rapid period of expansion. Starting around 10 to the power of minus 36 seconds after the universe's beginning, within just 10 to the power of minus 33 seconds, the universe expanded by a factor of 10 to the power of 26, equivalent to expanding from the size of an atom to the size of an entire galaxy in an instant. Following this initial burst of expansion, inflation slowed down considerably. Basic particles, atoms, and background radiation then came into play. This marks the onset of what we commonly refer to as the Big Bang. In other words, the Big Bang is not the universe's starting point. Instead, it signifies the end of the inflationary period. It's important to stress that the Big Bang theory doesn't describe the birth of the universe but rather its evolution. Traditionally, it was believed that the initial inflation had ended as the universe evolved to what we observe today. However, cosmologists' further research into the inflation theory suggested that this purported inflation might not have ceased at all, it might even be ongoing forever. This theory posits that our current home universe is just a small part of the entire inflationary region that has stopped inflating. For the broader inflationary region, there will always be areas still undergoing inflation. This is what the eternal inflation theory proposes. Within this framework of eternal inflation, whenever a region stops inflating, two new areas of ongoing inflation arise. Within these new areas, whenever one stops inflating, it gives birth to two additional areas of inflation, continuing the cycle. Thus, this process persists indefinitely. Hence, in the space beyond our universe and the universe of extraterrestrial beings, two types of regions exist: 1. Areas undergoing inflation, and 2. Regions that have ceased inflation. The areas undergoing inflation still hold the primordial inflating material and can be considered devoid of anything familiar to us. Conversely, the areas that have stopped inflating, which are similar to our universe, can be thought of as parallel universes to our home universe. These are what Tegmark referred to as Level 2 parallel universes. What sets apart these Level 2 parallel universes from the Level 1 parallel universes discussed earlier? First, Level 1 parallel universes, although far from us, still reside within the same eternal inflation universe as us, i.e., within the home universe. While reaching these other parallel universes might be implausible under ordinary circumstances, theoretically, if we could surpass the speed of light, it could be possible. However, this speed limit ultimately arises from the limitations of the speed of light. To exceed it, one would need to break this rule, which is currently beyond our reach. Yet, considering extraordinary means, we might still have the potential to reach these universes. Wormholes, for instance, operate through compressing or folding space, sidestepping the limitations of relative motion. Furthermore, if we could halt the universe's acceleration of expansion, full cessation isn't required, a bit like the ant on a rubber rope paradox. Given enough time, we could reach our destination. However, these methods wouldn't work for accessing Level 2 parallel universes. While these universes exist within the same eternal inflation universe as us, the distances between them, due to the expanding inflationary region, could be considered infinitely vast. These universes are like isolated islands, forever out of reach from each other. Beyond the question of accessibility, these two levels of parallel universes also differ significantly in appearance. While level 1 parallel universes share the same physical laws with us, along with identical fundamental constants, differing only in the distribution of matter and initial conditions, level 2 parallel universes possess the same fundamental laws but underwent distinct phase transitions, potentially possessing entirely different physical constants. For instance, the proportion of dark energy could differ, the strengths of the 4 fundamental forces might vary, and the masses of basic particles could differ from our world. These physical constants determine each parallel universe's appearance and influence their fate. Even a slight adjustment to these constants could result in a vastly different universe. Numerous parallel universes, due to such system settings, might not have the conditions necessary for forming stable space and matter. Most of these universes could end up eliminated due to their failure to burst properly. Comparing these parallel universes with our universe, which possesses just the right parameters, our universe's emergence and the development of civilization seem like a finely tuned coincidence. Whether this results from a selection principle, driven by some force or a higher power, is a question that lies beyond the scope of science. Whether level 1 or level 2 parallel universes, they remain parallel universes, entities that stand as prophecies within the framework of the inflation theory, entities that lack scientific proof. Science thrives on falsifiability, a criterion these parallel universes do not meet, making their existence impossible to test. Nonetheless, as a prophecy, if we could test the inflation theory that proposed them, in a way, this would serve as a test of the validity of parallel universes. Similar to Einstein's general theory of relativity, which predicted phenomena like gravitational lensing, time dilation due to gravity, and Mercury's orbital precession, phenomena that seemed inconceivable at the time but were later confirmed by evidence, parallel universes' authenticity might be validated through the inflation theory if we can test its predictions. The inflation theory seems to align with all current observational evidence. Does this mean that if the inflation theory is accurate, level 1 and level 2 parallel universes might indeed exist? Apart from the first 2 levels of parallel universes predicted by the inflation theory, Tegmark also introduced the 3rd and 4th levels. Given that these levels have transcended the universe's structure, let's leave them aside for now. The eternal inflation universe we discussed today already appears to be the largest structure in terms of the universe's structure. Yet, on second thought, if it lacks an exterior, how did the initial inflation occur? And what happened before inflation?